session.
Okay, we'll continue, and if it turns out that for the previous 10 minutes had no audio, then I'll fix it for people later. Add copy source test field, which is also, by the way, we're in index-space.h here. I'm searching our way. Oh, we'll get around to it. Okay, so a copy source test field is a structure which is basically, as I said, used to describe the sources or destinations of a copy. In the simplest form, so this is a structure with a bunch of fields in it, and it basically has setters to set the relevant portions of it for the common cases. So you almost never mess with the fields of this directly as a user. You'll call these methods instead to fill in a thing. So the general pattern is, if you know you're going to do a copy with 5 sources and 5 destinations, you will create 2 vectors of copy source test field, resize them both to 5, and then call these set methods on each of the elements of the 5 of the 2 vectors. So the most common one you're going to do is you're going to call set field. And so if you want to copy from a field, or certainly if your destination is always a field, then you're going to say, well, what instance is the field in, and what's its field ID? And again, these are Realm level instance and field IDs. Legion also has instance and field IDs, and it will translate from the Legion IDs to the Realm IDs here. Realm also wants you to know what is the size of the data you're copying. And this isn't always exactly the same as a field size. This interface is designed to allow you to copy even portions of a Realm field around if you want. So if you only want to copy the first 4 bytes of a 16-byte field, then you can set size equals 4. You can also, there's an optional parameter, set the offset. So if you don't want to copy the first 4 bytes, but the 4 bytes starting at offset 8, right, then you can do size equals 4 and offset equals 8 and talk about even one slice of a field. I don't think Legion ever uses this. I think Legion always copies the whole field, and so it gives me the whole size of the field here and just uses the default value of 0 for that. If you, I mentioned before indirections, if you want to make it indirect thing, then you set indirect instead of set field. And it's similar, except that instead of saying which instance you're gonna find the field in, you index into that indirection parameter and that's the thing that describes which instance or instances you're going to indirect into and how you're going to figure out which ones. Destinations, as I said, the destination isn't always just a copy, it could be a reduction. And so if you want to do a reduction operation, then you call set redop as well. So this is not mutually exclusive with either of the other two. And this will let you say which reduction op ID you want to use. Has Mike covered reduction operations for the difference between apply and fold? Or should I do a quick version of that right now? Anybody remember Mike talking about reduction operations?
So I actually don't remember that. Yes.
Okay, well, let me give the 10-second version, right? Which is that reduction operations, when you do a reduction operation in Legion or Realm, it's built to design. It's designed to allow for tree shaped reductions of it to the final value. So sometimes you are applying an update to the actual final instance, and sometimes what you're doing is you're doing what we will call folding together 2 values that still need to be applied to the final instance. And the reduction operation interface in Legion Realm is general enough that apply and fold are allowed to be different operations in some cases. The standard example I give is that if your reduction operation is a minus equal, then the fold operation is actually plus, right? Because if I want to do x minus equal y and x minus equal z, then I can write that as x minus equal the quantity y plus z. And so that's why you can't assume that apply and fold operations are always the same. So since Realm doesn't know whether you're doing one in the intermediate point of the tree or the final node of the tree, it asks you to tell you, are you doing a fold? Or if you're not doing a fold, then it assumes you're doing an apply. The other important thing you need to tell Realm is whether this is exclusive. And what that means is this the only copy that's going to be reducing into this field in this instance at the same time, or do you have other operations that are also doing it? And if you say that it's exclusive, well, then Realm will use the exclusive versions of the reduction operator, which often are written as read value, compute new value, write destination. But if you say it's not exclusive, then Realm will use the ones that are per element atomic. And so they are able to do atomic remodifier rates on each element. Right, that usually comes with some throughput overhead. So if you can arrange at the level of Realm operations that there's nothing else writing at the same time, then you go ahead and you set exclusive equals true, and Realm will use the faster code. But if you're not sure, or if you actually really want concurrency, then you let it stay false, and Realm will do, like I said, atomic adds or whatever based on the operator that you specified. Serialization, deserialization, I'm not going to cover today because it is pretty esoteric. But basically, imagine that the way the bits flow over the wire is not necessarily the way they're stored in the fields at the source or destination. Again, pretty uncommonly used, so I'm going to skip over it for now. But if somebody is curious about it later, I can follow up. The last method here that's useful is setting a fill value. So you can't use this for a destination, but for a source, instead of specifying an actual field, you can specify a constant value that will be applied to each location and destination. And you can do it two ways. You can either point at a blob of data and say how big it is, or there's a templated version where if you've got a float or a double or whatever, you just want to pass it by value, then this version effectively just is a wrapper around that version. So the most common forms you'll see are set field on both source and destination, occasionally set fill on the source for doing fills. You may see set indirection more and more in the future. And then reduction ops are pretty common too. Any questions on this? Like I said, we're gonna have a vector of these, n element, n copy source test fields in the source vector and n in the destination vector, and they're expected to match 1-to-1 between the two. Some particular realm does check that the size fields of sources I and destinations I match, and will complain if they don't. Okay, so that was the interface for the copy method. Now let's talk about where the guts of this are. So this is a subdirectory of Legion Runtime Realm called transfer, and so all of the non-module specific DMA transfer stuff in Realm lives in this directory. And the main two sets of files that matter are transfer.h and cc, which are kind of the fundamental building blocks of the transfer framework. And then we'll begin to touch on at the end of today channel.h and cc, which define individual channels that talk about the channel that actually knows how to move data from a given memory to another specific other kind of memory. But we're going to start with transfer.h first, because that's where the call stack goes first, which is in transfer.h. Actually, sorry, it won't be in the header because we declared the headers for it in index space.h. But those copy methods are actually implemented in transfer.cc. Maybe I should do that first. And I did apologize to the folks that came early that I'm not quite as well prepared as I should be today, so I apologize for any oscillating back and forth. But here is the body of that copy method that I was describing before. This is the version that takes indirections. I think the version that doesn't take indirections is actually just a simple template wrap around it that supplies an empty list for this thing. So this is the main entry point to the actual code. And again, in a top-down fashion, this is actually pretty simple, because what it's going to do is two things. First of all, we're going to take this description of a copy, so its sources, destinations, and directions, and actually what profiling we want to do. And we're going to build something called a transfer descriptor. And basically think of it as not just a literal copy of this, it'll be the thing that's able to reason about and optimize and remember the results of optimizing a given copy description. So we'll build one of those, and then we will create a transfer operation, which is represents the actual realm operation that's going to do one instance of this specific transfer. And it has the usual event machinery around it, right? So we're going to create an event that describes when this thing is finished. We will construct this object and give it both its precondition and the realm event that corresponds to finish. will tell it to either run now or wait if its preconditions aren't satisfied. And then we pass the transfer descriptor to the transfer operation, and so this is a reference counted widget, and so it's going to take ownership of it, which means we can let go of our reference, and then the actual transfer description will get deleted whenever the transfer operation is done with it. And then return the event, and at this level, that's all we needed to do. So if that makes sense, I will talk about transfer description next. And to do that, I'm going to hop back up to the header file. So we can look at what's in the transfer description. So as I said, it's constructed with basically the parameters from a copy call, what index space is being copied, sources, destinations, and directions, and profiling requests. It's reference counted, so you don't delete it directly. You add and remove references, and Realm will nuke it when it can. And I said the point of this thing is so that we can do analysis on the copy and make optimization decisions about how exactly to do the copy and possibly remember them. So in order to do that, there's this method called request analysis, which is the thing that basically says, please go do this, and you request it on behalf of a given transfer operation. The reason is if this thing is out, if you ever use the same transfer description for multiple operations, then effectively there's a race condition of has some other operation already requested the analysis. And so what this does is this requests the analysis, and if it's already done, then it returns true and says the analysis is there, go ahead and kick off whatever you want. If it's not done, then it remembers the transfer operation that cared about it, and it will actually automatically poke that transfer operation when the analysis is complete. The analysis uses the information about the index space and the instances, and so it can be that there's even preconditions on the analysis. You need to know the layout of the index space, which you don't necessarily know until the allocation is completed. You need to know the contents of the index space, which you don't necessarily know until that index space has been computed. You also need to know the layout of the instances that are being referred to, and those don't exist in full until both the allocation of that instance has succeeded and the metadata has been moved to this particular node where the copy is being analyzed. So there can be a number of things that have to be satisfied before we even have the metadata to do the analysis, and so that's what check analysis preconditions is doing. It goes through them all and makes sure it's requested all the metadata it needs. And if anything has to be waited for, then it waits for it, and then eventually perform analysis is where the main optimization process is performed. We've talked a little bit about the idea that in the case of faults or predication or speculation, we can have event preconditions that fail, which mean that they're poisoned, they will never succeed. And so we do need another entry point that tells the transfer descriptor that, hey, one of those preconditions is never going to succeed, which means this whole transfer description the analysis is never going to succeed, and therefore any copy that's dependent on it is never going to succeed. And this is the plumbing for that. Let's see what else is in here. This member data is basically just the original copy information, which we store as part of the constructor. And then once we do the analysis, we're going to fill in a bunch of other things down here. Since it can be requested multiple times, then this is how we avoid doing it more than once. If this is the operations we're going to poke when our analysis is done. And then the main place where we're going to remember what we decided as part of the analysis is this transfer graph object. So this is basically going to be effectively a compiled form of the copy that was requested.
Is this information cached on, like if somebody else asks for the same transfer later but builds a new object, would that graph be reused in that case?
No. So currently, if you ask for a single copy from Realm, then we don't keep a copy around because it would be a lot of effort to basically check that it matches the time before. So it turns out there's actually no case where we reuse the analysis right now. The case where we will reuse the analysis going forward is with Realm subgraphs. If you put a copy in a Realm subgraph that Legion can target from tracing, right, then it will be able to reuse that analysis across replays of the same subgraph. So some of this stuff is looking forward to when tracing is hooked up to subgraphs, and we can memorize the results of a copy that's going to be replayed multiple times.
Makes sense.
Okay. In theory, a realm level application might have enough information to know when it's redoing copies. But I guess even there, rather we can expose any way to control this from outside. The idea is, if you expect that a copy is going to be reused multiple times, then in the Realm API, the way to do that is to put it in a subgraph, and that's your placeholder for, I put this in a container for the explicit purpose of being able to talk about using it more than once. And so it's an indication that Realm should consider caching stuff. Okay, let's go talk about transfer graph then. And this is where I really had intended to have a picture, and I don't. And so I will probably draw a picture for next time and show it and describe it again, just so the pictures people are going to try to build in their head from this can be double checked. Okay, so a transfer graph, we said a copy is right, from the outside in. A copy is basically a list of sources and a list of destinations, and a request to please move all the bits from the right sources to the right destinations. I said in some cases, Realm will do those as separate copies. If there's stuff between different instances, then it'll probably just do separate low-level copies for those things. But if it's stuff that's in the same instance, then it may want to combine things together. The other case where things get combined together is with gathers and scatters. You might have something where we have to read data from potentially 4 different instances and move it to one instance where it gets written. And so you can get these complicated patterns where 4 different reads of different instances basically get merged together into one output. And so, as is often the case in computer science, almost any problem can be described as a graph, as a directed acyclic graph, and this is one of those things. So what the transfer descriptor analysis does is it builds a graph that describes the overall transfer we're going to do as part of the copy. And so a graph has nodes and edges. Sometimes I'll draw the picture where the nodes are the data and the edges are the movement between locations in memory. But the way the data structure here works is that the nodes are going to be individual single hop transfers from one memory to another memory. And the edges are going to be resting locations for memory, either actual source or destination location instances, or potentially what Realm calls intermediate buffers. So if you need to do a multi-hop copy because, let's say, a given GPU can't write directly to another GPU because you don't have GPU direct, then, and as we'll see the Realm path planner, the transfer plan will involve a multi-hop copy where the data is copied from from a GPU device memory down to system memory, and then maybe it goes over the network, and then it's copied from system memory on the far node back to device memory. And each of those intermediate hops needs to have some buffering, and so we call those intermediate buffers, and those can also be edges. So every edge is either okay, sorry, looking at the type. There's actually 4 kinds of edges. I talked about 2 of them. I talked about an edge that is an actual input or output instance that we're copying to or from. I talked about it's called IO edge, but basically this is one that's actually connecting 2 nodes in the graph and therefore is an intermediate buffer. The other actually, let me take it back. This is so I'm reminding myself how this looks on this code I haven't looked at in a while. From the graph perspective, they're all edges. Anytime data flows from one transfer object to another transfer object, it is going through an edge, and those are always intermediate buffers. Because the trouble with making the edges be the data locations is it means that you have nodes with edges that come into them that come from nowhere. So the input instance is actually an edge that goes into the first node without actually having an input node for that edge. Which is why it's a little bit weird. People don't usually draw graphs where edges dangle, but it's the way the data structure works. The reason it has to be that way is that an edge has at most 2 connections to it, like I said, it may have one, but it has at most two, which is the transfer descriptor that produced the value, and then the transfer descriptor that consumes it. Whereas the nodes in this can have multiple edges. And for example, in that gather case I was talking about before, we might be gathering from 4 different places and writing to one. And so if the data were the nodes, then you'd have trouble distinguishing between the same data being used for 2 different transfers or 2 different pieces of data being used in the same transfer. So in any case, maybe a little more rambling needed, but what we're going to build here is we're going to build a list of nodes, which are things that are actually going to perform data movement, and then edges, which are things that are going to either be original sources of destinations or intermediate results of some previous edge. And so to try to be a little bit more there's always big, when you're building data structures, do you nest the nodes and the edges, or do you keep 2 different vectors? And so the way this is implemented is we have a vector of nodes and a vector of edges, and then we use indexing to refer to, a node might refer to edges from this edge table. So a node, right? So this is what's called a transfer descriptor template. We'll talk about transfer descriptors in a little moment, but so since this is a plan that's going to describe potentially 1 or more instances of the copy, think of this as the template that will instantiate for each actual copy we do. And when we do a copy, each node is going to be what's called a transfer descriptor, which means that the node in this graph is a transfer descriptor template. And the things we need to know about it are what node is this going to run on, since we're going to do copies across multiple nodes. We actually don't, we hide most of the information about exactly what kind of copy. Is it a GPU copy? Is it a host copy? Is it an RDMA copy? Most of it is hidden behind this idea of, as you'll see there's transfer descriptor is a polymorphic class. And so instead of having different flavors of template for each kind, we just have a factory function that will build the right kind. And of course, we'll need to set this factory function properly. And I hope I'll be able to get a chance to do that today. But in the template, we just remember what the factory function was. For scatters and gathers and reduction ops, we need a little bit more information that tells us about, in addition to data actually flowing in a copy, with scatters and gathers, there can be control information. And so some inputs and outputs, or some inputs in this case, need to be special, and those are marked here. And then, as I said, each one has a vector of input edges and output edges. And each edge is either an actual instance, field of an actual instance, or is an indirection, or is fill data in the case of doing a fill. And so kind of similar to the copy source test fields, right? This is a flat structure, and then there's these constructors that build the various subtypes of it. We're deep inside of Realm internals now, so no user code is messing with these things directly. And then the most common case is that we're going to use a particular channel that I'll talk about in a bit to move data from one edge to another edge. And so here's a helper function that basically does it. Let's see, the last thing we need to talk about here in terms of what is stored in this transfer graph is that I said that intermediate edges require intermediate buffers. And so we need to build a list of what those intermediate buffers are so that we can go allocate them later. And so for each one, we decide what memory we're going to put them in. And even though this uses the Realm memory handle, it is always what's called an internal buffer memory, intermediate buffer memory, which is actually not exposed in the Realm machine model. There's separate memories from the application controlled ones. And the reason for this is that since the deferred execution model in Realm has the application running pretty far ahead and quite often exhausting all of the memory capacity of the application visible memories, we need to make sure that the DMAs, when they use intermediate buffers, have a different pool of memory that they can work from. And so those are called IB memories. And so these IB intermediate buffers are allocated out of that, and so we need to know which memory it is and which what the size of each buffer is. And because they're similar in a lot of ways to Realm memories, they use the memory handle. This similarity is actually reduced quite a bit over the years. So it's plausible that one day this is actually just IB memory, and we stop. Realm stops trying to think of IB memories as being a special case of memory and just thinks of them as being a different beast. In any case, though, as we build this plan, we may decide that we need to go through intermediate data, and we don't allocate right away because this is just a template. So what we need to do is we need to remember what are all the allocations that we're going to do each time we instantiate this template of intermediate buffer memory in each of the various places we need it. And importantly, as everybody knows, if you have something where you're going to allocate more than one resource and insist that you get them all before you make progress, you need to worry about deadlock situations. And so imagine two copies, one that wants to copy from node A to node B, and another that wants to copy from node B to node A, and each needs an intermediate buffer in each of the system memories for A and B. Right, if the A to B copy grabs all of the A's system memory, and the B to A copy grabs all of B's system memory, and then they both try to grab system memory from the other node, there's none left, and you deadlock. So the way we avoid this is that, just like people do with mutexes, if you can apply a total order to all of your mutexes and allocate them always respecting that total order, then you can guarantee that you never get the cycle that comes from somebody allocating something later in the order and then coming back and trying to allocate something early in the order. And so pragmatically what that means we do is we look at these IB infos and we compute an ordering of them in which the memory handles are strictly increasing. And we store that in this IB alloc order. And so we do that so that every time we go to allocate stuff, even though we know, these may have been listed in arbitrary order based on the shape of the copy, we know the order to do the allocation so that any number of different transfer operations that are trying to do their allocations can contend on IB memory without risk of deadlock. Okay, so that is the transfer graph. Let me now, in 15 minutes, show the rough, the high-level version of how that transfer graph is produced. So this is going to be in transfer description perform analysis. Okay. And I will say, going in, that this code is a massive amount of spaghetti, and a number of other folks on the Realm team have been actively improving functionality here. And anytime they refactor any part of this to make it less spaghetti-ified, I will certainly not complain about a bit. It grew, unfortunately, fairly organically, and with me not following good software engineering guidelines. And so this is not the only spaghetti in Realm, but it's some of the worst spaghetti. So let's see what we're going to do here. So again, we're not calling perform analysis until we know that all the metadata we're going to use exists and has been brought local to us, so that we're not going to stall as part of doing this this analysis. I mentioned some of the profiling you can do on memories is reporting not exactly when the copy happened, but information about the plan for the copy. And so, for example, you can ask, please tell me the source and destination memories of a copy and get profiling information. So we fill out a dummy version of this here, and then we'll fill it in more later. There's a special case at the top. If it turns out you ask for a copy that's empty, the domain is empty, well, then that's pretty easy. We actually skip all the analysis and just we still have to tell the transfers to pretend they did something. So we don't actually skip the transfer operations, but the transfer operations will have their own version of, well, actually, we give them an empty graph, which implicitly means that they don't have to do anything. So that was the easy case. The harder case is that there's actual data to copy. So we figure out how many elements we're going to copy. That shows up all over the place. If we're doing multiple fields and there's one or more fills, then instead of having fill data for every field, we combine all the fill data into one structure. And so that's what this code here is doing. so that we're not dependent on the source test fields. Then the next big thing we need to do is we need to decide what order we're going to do the copy in. So we're going to potentially do a copy with multiple hops, and we need to make sure that everybody agrees on the order the data is going to flow through any intermediate channels, which basically means we need to agree on what order we're going to iterate over the indices in the copy domain. And so that's what this method is doing. It's basically saying, okay, domain, figure out, given the sources and destinations and indirections, try to pick a copy order that is most friendly to the destinations and sources. And I'm not going to go into this code now because of time, but basically the short answer is, well, if it's one-dimensional, like it's easy. But if it's more than one-dimensional, then the basic pattern is look at the destination and try to pick an ordering that is most friendly to the destination. If the destination is unclear because it goes through indirections and the like, then at least look at the sources and try to pick an order that's best for the sources. If not, then just pick something. And the reason this matters is that there's two cases, one that's a very strong case and one that's a slightly weaker case. The strong case is, if I have a matrix that is in row major or column major order, and I iterated on it in the direction of goodness, so a column major order, if I iterate on columns, then each element I touch is contiguous, and instead of having to copy every element by hand, I can often find that the whole matrix is one big mem copy, and that's way better than doing each individual element copy by hand. Whereas if I go by rows over a matrix that's column major, then each element is its own discontiguous block of bits based on the iteration that I chose, and it's way less efficient in the copy. So ordering the dimension orders to capture contiguity is by far the high order bit. There's actually a second order bit, which is that if you are working on even if not contiguous, if you order things by ascending strides, then you're often being more friendly to your cache, right? If I do SOA, if I copy one field out of an array of structures layout, right? Then it may never be contiguous, but I'd still rather, do elements of consecutive structures in memory rather than hop around between wildly different structures in memory. So I guess that shows up if I had a 2D array of structures and I was only copying out one field, I'd still rather go through the structures in row major, in the natural order, even though it's not going to result in a contiguous copy, it's going to result in small strides, and I might get some cache line reuse. And in my experience, CPUs are way more sensitive to this than GPUs, but it doesn't hurt GPUs to do this either. Okay, anyway, what comes out of this is a dimension order, and this was decided over the entire copy. And so one thing that's a little bit inefficient here that theoretically we can improve over in the future is theoretically you could tell Realm that you want to copy two sources to two destinations. And maybe the source 0 and destination 0 are both row major, and source 1 and destination 1 are both column major. And you didn't realize this because the copy interface is agnostic to layouts. Realm will look at that and say, well, there is no order that's great for everybody, so I'm just going to pick one, and one of those two transfers is going to be really slow. We could try harder here. We have all the information, try harder and recognize that case. And instead of picking one dimension order for everything, we could theoretically pick different dimension orders for different disjoint parts of a transfer graph. If you have a transfer graph, parts of the transfer graph that are connected, all need to agree on the dimension order because, as I said, right, the information is going to flow through the intermediate buffers and you need to make sure everybody agrees. If one of my sources is going row major and other sources is going column major, then I can't zip those two together at the gather point potentially. So that's dimension order. Then there's one amount to a bunch of different cases for a bunch of different kinds of copies. And so I'm going to try to skim through them and get to the most important one. So like I said, there is, we do try in the AOS case, we do try to merge fields together. So as we iterate over the fields, we do check to see whether some previous field has absorbed this field. And so that's a quick early out. If that didn't happen, then we're going to do we're going to add some new stuff to the transfer graph. Let's see if we're doing, let's see, this is checking to see if there's reductions, and Sandy checking the reductions. If it is a reduction, right, then here's one special case that basically we don't merge together reductions. We do each reduction as its own thing. And so we know we're doing just one new source field, one new destination field. We figure out which memories those things are in. And then this is the next kind of comment. Well, this pattern you'll see in a bunch of different cases, so I might as well talk through it here. Once we figured out what the source memory, destination memory are, and we've chosen a layout, the next thing we're going to do is we're going to do what's called counting fragments. And the idea here is that some channels can only do contiguous copies. Like if I have something that's backed by memcopy, then it can only do contiguous copies. Whereas others might have the ability to be more efficient and do 2D or even 3D copies more efficiently. So for example, the CUDA driver API has 2D mem copies as a fundamental primitive. And if you ask for that, that's way better than doing a lot of separate CUDA mem copy calls. As a side note, it also has a 3D entry point, but unless somebody has fixed it in the driver recently, that 3D entry point is actually just a loop over 2D calls. And so Realm has learned that and doesn't ever try to use CUDA memcopy 3D because it's better for Realm to unroll it. However, if somebody were to write a custom copy kernel in CUDA and use that instead of the CUDA memcopy 2D and 3D entry points, then it could absolutely do 3D copies in a native way, and we would take advantage of that here. The trouble is, every different channel will have different rules for what kind of copies it can do well, and so we need to make a global decision of what path we're going to take. And so the first thing we do is we look at each source and each destination, and we ask it basically for each level of each dimensionality of copy, how many different copies would you have to do? And I'm calling those fragments here. So the first one is basically if all you had dimension 1 is if all you had is contiguous memcopy, right? How many different memcopies would it take to cover all the source data or all the destination data? And remember, it can be different for sources or destinations because one might be a different layout than the other. But we build a vector. So the first one is, if it's only 1D copies, how good can you do? The next one is, well, what if it's 2D copies? If we have CUDA memcopy, if we have a 2D memcopy, how many fewer fragments can you do by doing regular 2D copies? And same for 3D, and in theory up to ND, although I don't know of any interface right now that supports more than 3D. And the reason we're doing this is that the overhead of each separate copy can vary wildly from channel to channel, right? The overhead of calling memcopy is pretty small, and the overhead of calling CUDA memcopy is actually more like 2 microseconds. The overhead of doing a contiguous RDMA is one, on the order of 1 or 2 microseconds per packet as well. And so what we're looking for here is cases where basically what we're trying to do with this is we're trying to find channels that really don't like fragmented data, and as part of the path planner, we will consider doing an explicit hop to batch the data together into much bigger chunks before sending them over something that is not fragmentation friendly. And rather than recomputing that every time, we basically pre-built these fragment counts of how many fragments for each level dimensionality. And then when we go look at a particular path, we can just ask it, okay, what dimension copy can you perform? Okay, let's look up in the table how many fragments that would be and how sad that makes us. So that's going to be a standard pattern you see in all these things. Once we have that, we're going to call a helper function, which I think I'm actually going to end up talking about first thing next time, which is find fastest path. And this is basically the guts of the optimization. This says, okay, I now need to move data from this source memory to this destination memory. I may be serializing and reducing. I know how much data I'm moving, and I know how fragmented that data is. So please go do a path optimization problem through the different graph, right? Basically the machine model graph of how can data flow through the DMA system, and give me back the info that describes the best path for this data to take. Okay, and that path info is basically going to be of the form of channels, nodes, and edges to add to the graph. And so that's what this next code does. It basically says, okay, well, how many channels are there in the path info? Let's go add those to the graph, and it will say, which channels to use. And so this is where I mentioned before, we need to build a factory function. So this is where the path info told us which channel to use. We ask it to give us a factory object for that thing, so we can stuff it in a type agnostic pointer. We fill in information about which edges. This thing was a local decision of, okay, just this source memory, this destination memory on its own, what path you want to take. Remember, the transfer graph is a list of all the nodes and all the edges for all the transfers we're going to do. And so we need to adjust things based on, offsetting. So for example, we figure out where is it here? The starting index for which transfer descriptor template and which IB edge this path info is going to go into, and then all this code here is basically appending it to that list and making sure all the indices are right. It's mostly straightforward. A couple special cases just to make sure that the first and last edge in this copy are referring to actual instances, whereas the intermediate ones are referring to edges that are in the intermediate buffers, and so it has to do that. And I was talking about spaghetti. You'll see this exact same code about 7 times in here, and that's not proper software engineering. But I will use the usual example of I didn't have time to fix it later, and so now everybody pays ongoing cost for it until somebody gets around to fixing it and covers up my mess. Anyway, though. This was just the case where we're doing reductions, and so we planned it for one field. We record some more profiling information. I mentioned we talk about source and destination. We also can record what kind of copy it is and what the instances were and how long the path was. So these are things you can profile and you can see in Legion Prof today. The next case is if you ask for a fill, then this is encoded internally as the field ID being -1, and so we recognize that it's a fill, and we again plan a simple fill. And this is a lot simpler because there's no source, so this is just find a good way to either, if I've got something that can fill the destination memory directly, then do that. Otherwise, building a multi-hop path that can make the filling part actually just look like a store. So for an example here, if you tried to fill a file on disk, we don't actually, the file channel doesn't actually know how to do fills because it wasn't worth the effort. So instead, we build a multi-hop copy. We tell it, oh, you're just actually copying data from some other instance into this file, and then we the previous, and we do a multi-hop copy, and the previous hop is basically just filling up this intermediate buffer with copies of the same value. It's a little bit inefficient, but for things like file transfers, it's not the bottleneck, so it's a little bit easier to do it that way. For things like system memory and device memory, we have native fill operations, and so this get shortest path call will say, oh, there's one channel that can do it all for you, and life is simple. Again, more of that same copy code, and then the rest. So this is the case of basically no reductions, no fills. So this is the standard copy case. This one further splits between gather and scatter, but it also has code that it tries to merge fields together. And so this is where the first field we're definitely going to copy. We then figure out if we're gathering and scattering. If we're neither gathering nor scattering, then this is the standard vanilla copy case. And so it looks like the reduction case I showed you before, except that we do this pass over all the other fields and say, if anybody else has the same instances, the same reduction, and same sizes, then we will combine them into one copy that can be streamed together. And so that's what this code is doing. And so this is where if you see a copy that says it did 5 fields or 27 fields at once, it's because this loop merged over all of them. Once we merge them, then this code looks like the same I showed you before. We figure out fragmentation, figure out the fastest path, and then we go build the nodes and edges in the graph for that. And we're at the top of the hour, so I will next time talk about the guts of find fastest path, and then channels, and then if I have time, I will come back around to indirections, but that will all be next time. If there's super quick questions, I can wait a minute or two and answer a few questions. Otherwise, there's email, or you can save them for next time. But let me at least take a breath and let people ask a couple quick questions. or somebody can tell me, since I can't see the attendance list, that everybody's gone and left already, and I'm just talking to QuickTime and nothing else.
We're here.
Excellent. Do you have any questions, or are you saturated?
Nothing in particular.
Okay. Well, then why don't we call it a day for now? Thank everybody for your attention. And if this percolates or festers over 2 weeks and people have questions later, then we can certainly address them starting next time. Wanchan, why don't you go ahead and stop recording? Otherwise, when I stop sharing, the windows will change around on you.